Hi everyone, welcome to Lesson 2. This is our lesson on permutations today. We're going to start off with our question right away here, and this question is asking you, how many arrangements are possible for seating 3 of 7 children? Does order matter? So this here is FCP, Fundamental Counting Principle. You can solve it using FCP. So how do we set up FCP again? Well, if I'm only looking for 3 seats, seating 3 of 7, I'm going to look for 3 blank lines. And each blank line represents a seat, so that's seat 1, 2, 3, or however you want to label it. If you had 7 children, how many kids or how many children can sit in that first seat? You would have the option of all 7 who could have sat in that first seat. After that, well, how many kids are left or how many children are left here? You'd have 6 left, and then of course right here you'd have 5 left. Multiplying all these together, you'd get 210 different possible arrangements for seating 3 children out of 7. The question here, does order matter? Order does matter in this case. So order matters. Reason being is there's no repetition of children. You can't have more than one child in a seat, so order matters. That brings us to the idea that we're going to be working on today, permutations. Permutation is an arrangement of a set of elements in which the order of the elements is important. So again, order matters basically. For example, a locker combination, the one that you have in your hallways there, should in fact be called a locker permutation because the order of those numbers matter. They go in a certain order for you to unlock that combination locker. We do have a general equation here as well that we can use to figure out permutations. This equation says NPR. So the way I would read it is N pick R and P or N perm R, however you want to read that there. This equation basically translates to n factorial divided by n minus r factorial. Okay, where n is the number of items that you have and r is at time taken. So this is your total versus how many you need. So in the previous question, if our total was 7, it'd be 7 permutate 3, and then you'd end up with 210 as well. We're going to take example 2 here and evaluate 9 perm 4. So on my calculator, what I'm looking for is my perm button. So here I just have my calculator loaded up. You could type the following buttons to evaluate this question here. So what I would do is type in the 9 first, math, scrolling to the left this time. You're trying to get to that probability box, scrolling to the left 2, and it's going to be option 2. On my calculator, it defaults in that P right away. 4 is our other number. Hit enter. There we go. We have an answer of 3024. A shortcut to doing the exact same thing to bring up that menu is if you hit alpha, your Windows option, and you have that exact same option right there. It'd be option 7. You can choose option 7 and then fill in your same blanks. It'd be 9 and 4, and of course you get the same answer there. Okay. So right away, using our calculator, evaluating this, you have an answer of, switch colors, your answer was 3024. But let's do this the long-handed way. Let's also use our equation here to see if we can make sense of it. So let's write out our equation again. So we have 9p4, 9 perm 4. That's the same thing as saying n factorial, which is 9 factorial in your numerator, divided by 9 minus 4 factorial after that on the end there. So this here, let's just clean up our denominator, is 9 factorial divided by 5 factorial. Because of course 9 minus 4 is 5. From here, because we have our 9 factorial and that's the larger factorial up top, I'm going to decrease that until I get to something that matches the bottom. I'm looking at about 5 factorial. So I'm going to go 9 times 8 times 7 times 6 times 5 factorial, and here's where I stop because I'm going to divide off 5 factorial from the denominator. So these two simply cancel out. That leaves me with 9 times 8 times 7 times 6, which also is the same thing as 3024. So two different ways to do this. So one, using your graphing calculator, or two, simply evaluating using your equation here. In example 3, we have how many different assignments of 13 soccer players to 11 different positions are possible. So here, what's our total? So our total is 13, so that's going to be the letter N. And our R, we're only looking at 11 of them at a time. So if I set up an equation, my equation is going to be 13 permutate 11. And again, I could just type this in on my graphing calculator here. So again, I'm going to go with the 13 first, alpha window, option number 7 there, 11, enter, and then that's going to be my final answer. So we're looking at 3 billion, it looks like. So I have an answer of 3,113,510,400. So that there, nice long answer right there, same answer there. So again, straight off of our graphing calculator. But could you have done this differently? Of course you could. So another way to do this is if you'd use the equation. So again, we would have something that looks like, instead of just using your graphing calculator, you'd have 13 factorial divided by 11 factorial. And here, this is the same thing as saying 13 times 12. All of that is divided by 11 factorial. Ooh, not 11 factorial. My apologies. I am missing my subtraction. Ooh, that was way too big. Let's try that again. So this is now going to be 13 minus 11 factorial, which of course is just 2. And so you'd have to drop this all the way down to 2. So 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, and of course 2, and all of that there, division symbol, factorial there. Our factorials would cancel out, and you'd get the exact same answer. But let's take a quick pause. What does this numerator look like? Well, we have how many positions? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 positions there, stopping at that 3. So is there a third way to do this exact same question? Yes. To evaluate this question, you could have also used FCP. And you would have had 11 blank lines starting from 13 going all the way down to 3 there, and of course you get the exact same answer. So one question, multiple ways to approach it, however you want to approach it. You can practice and get to that answer. In example 4 here, we have how many words can be made using one or more of the letters from the word wind. Well, first off, how many letters do we have here? We have 4 letters in the word wind, and we also have the keyword in our equation here. The keyword is the word or. And if you can't remember what or means to add. So you're adding up a few options. You're adding option of 1 letter or 2 letters or 3 letters or all 4 letters. So we're going to add on a few options. So how many words can be made using 1 letter? So let's start there, that case there. So it'd be 4 permutate 1, because out of the 4 letters you're just picking 1 letter. Or, and or means add, or, and we're going to add on or more. So let's do the or more. So we got 4 letters, perm 2 this time. 4 letters, permutate 3, and of course 4 letters, permutate 4. Can't go past this because you only had 4 letters to choose from. Okay. So here you'd just evaluate each piece on your calculator, and this would get you to a total of 64. Is there another way that we could have did this exact same question? Yes. Again, we could have approached this using FCP, Fundamental Counting Principle. So again, in the first case it says using one, basically our first case is using 1 letter. So if you had first blank line, 1 letter here, how many options for that 1 letter? You'd have all 4 options there. And then it says or, so we're going to add on. Well, what happens if you had 2 letters? Well, that's going to be 4 options for that first letter, 3 options for the second because you couldn't have that same letter again. Plus 3 letters this time. So that's going to be 4 times 3 times 2. And of course, we're going to add on that last one if we used all 4 letters. So that's going to be 4, 3, 2, 1. Knowing that these are all multiplication in between, if I did a quick evaluation, this is the same thing as saying 4 plus 12 plus 24 plus another 24. And there you go. If you added all this up, this still gets you to the answer of 64. So again, 2 different ways to do this, 1 using an equation or 2 using FCP. In example 5 it says, if there can be any length, how many words can be made using the letters from the word Spain? So here, any length meaning you could use 1 letter, 2 letter, 3, 4, or even at most 5 letters there. Again, you could use FCP to do this or use your equation. I'm just going to opt to use the equation this time. So for the first word, we have 5 letters to choose from. We're going to pick one of them. Then the second word will be 5 perm 2. Then 5 perm 3, and so on and so on. And here, that's going to be my setup. I can evaluate each piece individually, and let's see what we get. 5 pick 1, just 5. Then you'd have 20, 60, 120, and another 120. In total, you'd have 325. 325 possible words that could have been made of any length. We have a quick note here before we move on. Our note says, why does 7 pick 6 and 7 pick 7 the same thing? And if you go back, why is 5 pick 4 and 5 pick 5 the same? Why is 4 pick 3 and 4 pick 4 the same? And this is probably the best example right here. 4 pick 3, you would have had all 4. So 4, 3, 2, and you're missing one more position. If you had 4 pick 4, it'd be 4, 3, 2, 1. Well, 1 times anything, still the same. That holds true for something like this as well. So if you had to go in descending order, it'd be 7, 6, 5, 4, 3, 2 is equal to 7, 6, 5, 4, 3, 2, 1. And again, that multiplying that extra 1 doesn't really change anything. If you did this in terms of an equation, you'd have the following. So let's just flip it in terms of an equation. You'd have 7 factorial divided by 7 minus 6 factorial, and that's going to be set equal to 7 factorial divided by 7 minus 7 factorial. Well, here, what is this? Well, this is the same thing as saying 7 factorial divided by 1 factorial, which is equal to 7 factorial divided by 0 factorial. If you evaluate each piece 1 factorial and 0 factorial, both of these are equal to 1. So let me just show you that. So if you had 1 factorial, and that's option 9, that's equal to 1. And if you had 0 factorial, they're both equal to 1. The question is, why is 0 factorial equal to 1? Well, even if you have 0 there, that's still considered one option. It's the option of 0, option of nothing. So basically, your denominators are 1 and 1. That means your numerator is 7 factorial, 7 factorial, so these are just equal to each other. Okay, so again, that's using our calculator and using our equation, and the big key here, and I'm going to put a star next to this, 1 factorial equals 1, 0 factorial is also equal to 1. And that was the key here. In number 6, we have how many different arrangements of the word boardwalk are possible. So first off, how many letters do we have in the word boardwalk? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 letters in total. So let's quickly jot that down. We have 9 letters total. This question is the first time that we see repetition. In our other words, we did not see repetition. Each letter was unique. In this case here, I see repetition. I see this letter A, and I see another letter A here. So I have two A's out of these 9 letters in total. So in this case here, with repetition, we just have to do one extra step, but shouldn't take us too long. So let's start off with this. How many different arrangements of the word boardwalk are possible? So assuming that we have to use all 9 letters for the word boardwalk, it would be 9 permutate 9. But in this case here, I'm going to divide off 2 factorial. And this divide off 2 factorial, this here is a quick note. This is because of your repeating letters. So divide off repeating letters. Why 2? Because we had 2 A's there. So if we wrote this out here, let's see what we get. So this here would now be written as 9 factorial divided by 9 minus 9 factorial. All of that's divided by 2 factorial. Of course, that's just 1, so that kind of goes away. So you'd have 9 factorial divided by 2 factorial overall, which is the same thing if you evaluate top and bottom. This here is 362,880, all divided by 2. And that brings you to a total of 181,440. So that's how many different arrangements of the word boardwalk with the 2 repeating letters are possible. In the next section here, we have the equation here, and this is just what we just did previously. Here's the equation for dealing with repeating values. It's going to be n factorial divided by all your repeating values. So again, denominator is your repeating values, and your numerator is your total letters, or total of whatever that is. In example 7, we have Gary wants to plant 8 trees in a row on his acreage. 2 are pine, 3 are elm, 3 are birch. How many different arrangements are possible? So just using our equation, how many total trees do we have? We have 8 factorial, because that's our total. We're going to divide off all of the repetition. So we're going to divide off the 2 factorial, 3 factorial, 3 factorial. And again, I'm just going to go straight to my graphing calculator here. I'm going to use a fraction function this time because we have a fraction. So I'm going to go in the numerator. That's going to be 8 factorial divided by 2 factorial, which of course is just 2 by the way, but I'm just going to leave it as is. 3 factorial. And again, 3 factorial is 3 times 2, which is just 6. And another 3 factorial. And again, that's another 6. In total, 560. Alright. Could you have written this slightly differently? Of course, this could have also been written as 8 permutate 8, because you have 8 trees in total and you want to pick all 8 to plant, dividing off your repetition. There we go. So 2 ways to get to this exact same answer.